In our next example, we're going to take a look at a baseball player running from home to first base. So a baseball diamond is essentially the shape of a square, and it's a square with side length of 90 feet. So we have 90 feet here, 90 feet there, 90 feet here, 90 feet there, and then we have the home plate, first, second base, and third base. So we have a player running from home to first base at a rate of 20 feet per second. So the question is, at what rate is the distance between the player and second base changing as a function of time? Well, at the moment in time when the player is, let's say, halfway between home and first base. So at the moment when the player is halfway between home and first base, what's the rate of change of the distance between the player and second base? So what's the rate of change of the distance to second base? Okay, so let's first think about what the distance would look like. Well, the distance is going to be, do green, the length of this line right there. So that's a distance. So we'll assign our first variable, we'll call it capital D for distance. So capital D is the distance between the player and second base. And then let's call this one capital F. Actually, let's call it capital S. Let's be a little different. Capital S for second, capital F for first. So capital F represents the distance between the player and first base, and then capital S is the distance between the player and second base. So we've defined our variables. We have F and S. Now we're given that the player is halfway between home and first. So at this moment in time, F is going to equal 45. So this is only at this moment, right? Because the player is running from home to first. And then of course we can also solve for S at that moment. And then also F prime, df dt. Now this is where we have to be really careful with these rates of change. They said that the player is running to first base at a rate of 20 feet per second. So F prime is not equal to 20. It's equal to negative 20. Because remember, F is defined as the distance between the player and the base. And as the player is running this way, the distance is decreasing, so df dt needs to be negative. So whenever it gives you a rate of change in the problem, I mentioned this in my strategies video, I'll mention it again. Whenever a rate of change appears in your problem statement, you always want to take a second and say, is that going to show up as a positive or a negative derivative? Because usually they describe the situation in words, such as the player is running to first base, and F is your own variable. I mean, maybe somebody else might have used the variable H, which is the distance to the home base. So, our variable is F, and F is going to be decreasing, so F prime needs to be negative 20, not positive 20. And then at this moment, S is, so the trick now is that we have a right triangle, because this is a right angle. So we have a Pythagorean triangle right here. So Pythagorean's theorem tells us 90 and 45. 90 squared plus 45 squared is 10,125. So square root of that. So basically S at this moment is the square root of 10,125. So these are the instantaneous values for the variables F and S. The only one that's a constant is this. The distance between first and second is always a constant. So at any moment in time, we get a relationship. F squared plus 90 squared, which is 8,100. So F squared plus 8,100 is going to equal S squared. So this holds in general because of Pythagorean's theorem. So to figure out what ds dt is, which is what the problem's asking for, what's the rate of change of the player's distance to second base? So what is ds dt? We have to differentiate this with respect to time. So the derivative of f squared is going to be 2f df dt, and that's going, derivative of 8100 is 0. Derivative of s squared is 2s ds dt. So we can solve for ds dt. We know f, we know the current value of f, we know df dt, and we know the current value of s. So ds dt is going to equal f over s df dt. Right, so I'm going to cancel out the 2's and then divide through by the s. So f over s df dt is equal to ds dt. So f over s, so f was 45 divided by 10,125 square root, and then multiply that by df dt, which is negative 20. So the s dt is going to be negative 8.94427 feet per second. So basically, even though the player is running at a rate of 20 feet per second, his distance to the second base is only decreasing at a rate of approximately 9 feet per second at that moment in time. So obviously, this relationship here depends on the relative ratio of f to s. So as the player moves, the ratio of f to s is going to change, and so will the rate of change of the player's distance to second base.